Alright, this video is going to be tough for me because I'm going to have to force myself to do some things very rigorously and very annoyingly in like this way that some teachers make you do these problems. But this is just different teachers have different ways of making you like sort of write out the work of doing U substitution. In the previous video, I sort of showed you how I do it, where I sort of look what do I think the U should be. I figure out what DU should probably be and just I visually look and see if they match up. And I'll show you that in a second. So each of these problems I'm going to work in the three different ways that I've seen: my way, the slightly more rigorous way that most teachers do, and then the crazy way that some teachers do. And that's the one that's going to be really hard for me, but I'll try and get you through it. Teachers do give take off substantial credit sometimes if you don't show all your steps the way that they want you to show your steps. So you really got to figure out which one of these ways does your teacher do it, and find out if you just ask your teacher point blank, hey, if I do this on the test, do I have to do all those steps, or if I just get the right answer and show my work, is that enough? Because honestly, when it comes to understanding calculus, my way is the best. The mathy way is kind of decent, but the crazy way is totally idiotic, and I don't know why anybody does it. So hopefully I'll be able to get through this video in one piece, but we'll see, because that crazy way is just, ugh. All right, here's the deal. So here's how I would work this problem. I look at this thing and I say to myself, and I think we had the same problem in the previous video, I say to myself, it looks like a power rule situation, because you always know that some stuff's going to go away. So it looks like the primary thing that's going on is that I have x cubed plus 1 to the fourth power being pretty obviously a big exponent. So I'm hoping that this is my du and it's going to go away, and then it perfectly matches this. So what I'm going to do is I'm going to say, you know what, for this problem to work out, I think my u is going to be x cubed plus 1 so that I can do the power rule. And then, but if my u is x cubed plus 1, my du is basically just the derivative of this. It's going to be 3x squared, and the derivative of 1 is nothing, so it's just 3x squared. And then I'm going to throw a dx on there just because there's always a dx. So I basically know that for me to use the power rule on this, I've got to have a 3x squared dx waiting for me right next to it. Oh, and look at that, sure enough we do. So all that's happened is I've just verified, you know what, I can use the power rule the way I'd hoped to. And here's the power rule up here. So I would just immediately write down the answer. I would go to, I know the answer is going to be the same stuff to a higher exponent. So now it's going to be x cubed plus 1 to the fifth power instead of the fourth. And I divide by the new power. So this is all over 5. And add a c to it, and I'm done. Bam. So this u and du stuff I just did, that was only a way to double check that the problem was doable. But I wasn't like really doing a lot of math on it. All right, so here's the mathy way that most teachers will have you do when you do this. So they're going to do the same thing as far as u. They're going to say, you know what? Yeah, we're going to use the power rule, and therefore u is x cubed plus 1. And your du, therefore, actually they'll call it du over dx probably, because technically it's like an implicit differentiation situation. Anyway, so they'll end up with 3x squared. Then they'll say, well, if you look at the formula, you want du. You don't care about du dx, you want du. So they'll literally multiply both sides by dx at this point to get 3x squared dx, which you'll notice is something I just pretty much did in my head, because there's always a dx, so I'm like, who cares? All right, so at this point they've got the same step right here that I had right here. But you see that I just jumped straight to the answer. I was like, oh yeah, we have 3x squared dx, so let's just integrate with the power rule and be done with it. But here's what this teacher makes you do. They make you rewrite the problem in terms of u, not x. So at this point they're going to make you rewrite the problem, so there's my integral sign, and then x cubed plus 1 was u, right? So this is really, the problem is u to the fourth. Because if you have your u raised to the fourth power, that's really just u to the fourth if you sub in u for x cubed plus 1. And then that 3x squared plus, times dx, they're going to say, well, look at that. That's right here, and that's just du. So we've transformed the problem now to an integration of u's, which makes a little bit more sense once you've done it a few times. But the point is, now we've got it in terms of u's, and now it exactly looks like this problem. So that's, I think, the reason they do it, is to make the problem look exactly like it was nothing but u's. And now it's really straightforward to use the formula up here on the upper right. So integral of u to the fourth is just u to the fifth over 5 plus c. But of course we're not done, because the problem probably shouldn't be in terms of u, it should be in terms of x. So now they've got to sort of unsubstitute again and just stick back in u, x cubed plus 1 instead of u. So at that point, they would replace this u right here with x squared plus, or x cubed plus 1. And of course, it's got a fifth exponent, and it's over 5, and it's got a plus c. So you can see that ultimately they got to the same place I got. They just had this intermediate series of steps where they got rid of all the x's and replaced them with u's. So it really was u substitution. I guess that's where the name of this technique comes from. All right, so that's not so bad. They threw in a couple extra steps in the middle. Not too shabby. With definite integrals, which we'll see in a couple of minutes, that adds a little bit more busy work to that problem, but basically it's fairly straightforward. You just got to sub in and turn everything into u's, kind of in the middle of the problem. Here's how the crazy people do it, and all right, so let's take a look. So once again, the crazy person is going to say that u equals x cubed plus 1. That's the same. Then they're going to do the same next step as the less crazy person did, and they'll say, okay, so that means that du dx equals, 3x squared. Then they'll multiply both sides by dx, so they'll get that du equals 3x squared dx. All fine so far, right? So right now, we're exactly here. We haven't done anything differently than the previous person did. Here's where they get nuts. They say to themselves, you know what? Let's solve for dx. So instead of subbing in, instead of saying, you know what, this is all du, let's just replace it with a du. What they say instead is, let's solve this equation for dx. So they get that dx, they divide both sides by 3x squared, and they get dx equals du over 3x squared. Follow me so far? They've deliberately made an equation that has both u's and x's in it right here, which I think is kind of nuts, obviously. But all right, so why'd they do that? Because now they're going to take this, and in the original problem where they have a dx, they're going to replace it with du over 3x squared. So now their problem's going to look like this. Integral x cubed plus 1. So I'm just recopying the original problem here. But then and then we have a 3x squared still. But then this dx here, the last thing on the right, they're going to replace with du over 3x squared. Now, why did that make any sense at all? Look at what just happened there. The 3x squareds cancel. And of course, now they have du's. They're like, you know what? Let's replace that x cubed plus 1 with a u also. So now they've got it down to u, integral of u to the fourth du. At this point, they're in exactly the same position as this person was right there. So this step and this step are identical. Why'd they go to the trouble of subbing in for dx and all that? They just did it so the 3x squared would cancel. So there's a totally superfluous step. The middle way involved that same substitution but didn't do any crazy canceling. And the middle way was better, as you'll see in the slightly harder problems. The middle way is actually way easier than this crazy way. The crazy way makes it really hard to see what's going on. At this point, the crazy way is just identical to the middle way. All right. In that particular problem, we already had our du and our u matching up perfectly, so everything was pretty cool. All right, so here's a problem we did second in the first video, the video before this. So Chris's way is, hey, you know what? This looks like a cosine integral formula. So I'm going to write down the cosine integral formula. And you can see it has some u's and some du's in it. So the first thing we have to do is identify our u. You know, what's the cosine of? What's the u? Well, it looks like it's 3x, right? So I'm just going to write down that u equals 3x. And then, of course, because the whole point of this is to see if my du matches, I'm just going to take the derivative, and I'll get that du equals 3 dx. Now you notice that, all right, so if my du equals 3 dx, that means that right here next to the cosine of whatever, I'm going to need a 3 dx. But I don't have a 3 dx, I just have a dx. So I basically need a 3 right here. So the Chris way, I'll just rewrite the equation here because I'm going to mess with it. So cosine of 3x dx, Chris's way says, you know what? I look at this and I've got a dx, but I need a 3 dx. So because they're pretty close to matching, they're just off by a constant, I need a 3 there, so I'm just going to put a 3 and put a 1/3 out front. That's it. So now I've got a 1/3 out front, but now this is all copacetic. This is all good. Everything matches. So because my du and my u match, I can just integrate this and I just keep my 1/3, then I get sine of the same stuff plus c, and we're done. All right, so that was Chris's way. What's the mathy way? the way that your teacher will probably make you do it, at least at first. All right, so that person also says, hey, we want to use the cosine formula, so let's set u equal to 3x. Then they'll say, hey, you know what? du over dx equals 3. Multiply both sides by dx, so they get du equals 3 dx. So then they look up here, and they realize, uh-oh, we need a 3 that we don't have. So they'll do the same thing I did right here. They're going to put a 3 here because they need it, and then they'll put a 1/3 out front. The only difference is that now they're going to add that step where they turn everything into u's. So at this point, the math teacher and me are in total agreement. We've got the same problem going. They're just going to now rewrite this as 1/3 of cosine u du. Then they'll integrate that and get 1/3 sine of u plus c. And then they'll convert back and get 1/3, they'll substitute back in. For the u, they'll replace it again back with the 3x it equals in order to get everything back in terms of x. And just a side note here, this 1/3 and the 3, those don't cancel because the 3 is in there behind the sign. You can't just cancel it willy-nilly with coefficients out front, so just as a reminder. All right, so we got the same answer. Once again, the only difference is that they sort of replaced x's with u's in the middle of the problem, but then they undid that, so they end up at the same place at the end that I would end up. All right, here's where the crazy person actually, okay, let's see what happens. So they're going to go u equals 3x, just like everyone else did, which means that du dx equals 3, which means that, now remember, these people are crazy, so what they're going to do is they're going to move x up to dx up to here, so they'll get that du equals 3 dx. But then in this case, they're solving for dx. So you're going to add this funky step where they divide both sides by 3, and they get that dx equals du over 3. Now there's the one point where I applaud these people because watch what happens. They're now going to rewrite the problem subbing in for dx. So where we had a cosine 3x, they're going to write cosine of u, since u and 3x are the same thing. And then for dx, where we had a dx in the original problem, they're going to write du over 3. Honestly, that doesn't seem that crazy now, because watch what happens. They've now got an over 3, which we didn't have in our problem, because we had a 1/3 out front. A 1/3 out front and a 3 underneath are exactly the same thing. Either way, you've got a 3 in the denominator. So what they're going to do at this point is say, oh, you know what? We're dividing by 3. Let's just move that out front out of the way so it doesn't confuse us. And then let's integrate this. So we'll get 1/3 sine of u plus c. And then, of course, they sub back in the 3x. All right, so that's the crazy way. I call it crazy. In this case, it actually made a little bit of sense. It sort of created that 1/3 for us automatically instead of us having to worry about it. The problem is with the crazy way, they sort of never explain what's going on. So you're sort of lost in the dark. And on harder U-sub problems, the crazy way is really confusing. And I've never seen a student who could really pull it off until they had mastered it doing it this way, and then sort of added that level of complexity doing the crazy way. So basically the point is that I've never seen anyone do well with the crazy method unless they learned one of these other two methods first and then did it the crazy way. If I'm ever tutoring someone whose teacher does things the crazy way, first I show them Chris's way because it generally makes intuitive sense to more people, and then I say, and by the way, here's the math you're going to have to write down, the busy work you're going to have to do to like get full credit from your teacher. But the point is, the crazy way, it has its perks. It generates the 1/3 automatically, but on harder problems, it just gets really confusing and can make it impossible to figure out how to do the problem. All right, so some problems can't be done. I'm kind of giving that away up here. But recall that the first step of any integration problem is sort of identify your u and see if it matches up, right? So Chris's way is to say, you know what? This definitely looks like a power problem. I got some stuff to a high exponent. There's no way I'll be able to do anything besides a power rule. So let's see if that would work out. We're just going to do, obviously, if it's the thing that's being raised to the exponent is u, that's going to be x cubed plus 3x, which means my du is going to equal the derivative of this stuff, which is 3x squared plus 3 times dx or whatever. Here's the problem. I don't have any of that stuff. I don't have an x in front of the dx. I don't have an x squared. I don't have any of this stuff. The 3's I could make up. I could throw a 3 in front of here and then put a 1/3 out front. That's good, but I can't conjure an x squared from nothing. So at this point, Chris's way is to walk away, because this just is not integratable. The only thing you could do is FOIL this out 5 times, and that's going to be a horrible mess, right? You could use binomial theorem or whatever. Turn this into a massive polynomial. It looks like the highest exponent would be 15. It'd be x to the 15th and da-da-da. So if you turn this into expand it into a massive polynomial, you could integrate it term by term, no problem. And this u sub stuff wouldn't affect you. But I'm not going to do that. I'm just going to walk away. So this is not integratable using u substitution. Is the bottom line. Maybe we could find another way, but u sub won't work. What's the mathy person going to do? They're going to do pretty much the exact same thing. Because remember, the mathy person, they're doing that extra step of u substitution busy work in the middle of the problem, but the beginning of the problem is the same. You need to look at your u, look at your du, and see if it matches up, and it just doesn't. So they won't be able to do the problem either. But here's what the crazy person does. And this is why crazy way is not good, because when you get to harder problems, you won't realize that it's hosed until later. So the crazy person is going to say, you know what? They don't think, they only execute. So this person's going to say u equals that, so du dx equals, oops, don't need that last second equal sign, 3x squared plus 3. Then they're going to multiply both sides by dx. Then they're going to solve for dx, so they end up with dx equals du over 3x squared plus 3. Now they're going to substitute that back into the original problem. So they're going to say, all right, so the original problem has become that 1/3 and 3 obviously it's made up, so that's not there. So the integral of u to the 5th times, and then for the they're going to replace the dx with what they just got dx equals. So they're going to replace the dx with du over 3x squared plus 3. At this point, someone who is really good at this method, or maybe their teacher who thinks this is a smart way to go, would look at this and say, oh, clearly you cannot integrate this because you have x's and u's. That doesn't make any sense. Ha ha ha. And the only time this method works is when this cancels perfectly. If this 3x squared plus 3 canceled a 3x squared plus 3 in the numerator, then you just have u's and it would work out. The problem I see is that when students get to this point where they've got a u to the 5th, a du, and then a 3x squared plus 3 downstairs, there's a lot of different responses that students have, but they all result in confusion and panic. You're either like, oh, so now it's a rational problem and they start trying to integrate a quotient type situation, or they just do the power rule and then just leave this in the denominator of the problem. There's all kinds of things you can attempt to do, but they're all wrong. Basically, you're hosed, and you can't do this with u substitution with a crazy way any better than you can do it with the other ways, just that the crazy way, yeah. So basically the moral of the story is, after you find your u, the way you should do these is after you find your u, find your du, just take the derivative of u and get this thing, and then you got to see if everything here is up here. And if it's off by more than a constant, if there's any x's missing or exponents missing, you're just kind of hosed and you have to move on. You just can't do the problem. All right, so that's indefinite integrals. And as you can see, I obviously prefer my method because I think it makes more sense. But the mathy way wasn't so bad. Now the mathy way is going to get a little bit different with definite integrals. And I'll show you why in a second here as we go through this example. But basically, during that whole portion of the problem where you replace things with u's for the mathy way, we're going to change the limits of integration on this definite integral. All right, so let's do Chris's way first. Obviously, there's a power rule situation. We got some stuff raised to a power of 2. So I'm just going to say u equals x cubed minus 5. Therefore, my du equals 3x squared dx. And then I'll look up here and I'll say, oh, indeed, I do have an x squared dx. The thing I'm missing is a 3. So I need a 3 in here, and therefore I need a 1/3 out front. At this point, I've just sort of squished those into my problem, and I can go ahead and integrate. So I would say that this is the integral of 1/3, and then my u, which is x cubed minus 5, to a new power. So it goes up from 2 to 3, which means I divide by 3. And now I don't need a plus c because it's a definite integral. So I just go from 1 to 2. And at this point, since I have 1/3 and 3, I'm just going to combine that into 1/9. So it's going to be 1/9 times x cubed minus 5 cubed, evaluated from 1 to 2. Alright, so as you can see, I've just got x's, I got my limits, I can just plug them in. So I get 1/9 times x cubed minus 5. Let's see, if I plug in 2, I get x cubed is 8, minus 5 is 3, so I get 3 cubed. And I subtract, now what happens when I plug in 1? I get 1 minus 5 is negative 4, negative 4 cubed is negative 64. So I got one negative from evaluating it, but then I got the negative that comes with definite integrals. And these two negatives cancel out each other. So I get 1/9 times 27 plus 64, which equals what? 1/9 times 60, 70, 91. And 91 is not divisible by 3, or 9 for that matter. So I'm just going to get 91/9. Shoot me an email if that number is incorrect. Oh, don't. Let's see, 2 and 6 is 8, 7 and 4 is 11. Yeah, 91/9. Okay, so that's what we get my way. What do we get the mathy way? Well, as usual, we start with the same thing. So it's x cubed minus 5, which means your du is 3x squared dx. And at this point, the mathy person, just like me, will say, you know what, we have x squared dx, but we need that 3. So they'll stick in the 3 and they'll put the 1/3 out front, just like we did in the previous version. Alright, so here's where they're going to get a little bit wackier though. They're going to rewrite this in terms of u. So they're going to rewrite the original problem. They have that 1/3 out front now. Then they've got u squared, and then they've got du, because they just replaced that 3x squared dx, which is right here, with du. Alright, so they would be ready to integrate. You'll notice though I forgot to do something, or at least I left it out because I wanted to explain it to you, and that is changing the limits of integration. So the mathy person says, you know, the original problem, this 1 and this 2, what that was saying is that x goes from 1 to 2. Makes sense, right? But the problem is that now we've replaced x's with u's. And u doesn't go from 1 to 2. U goes from something to something else. Those numbers are going to change, because just because x is going from 1 to 2, who knows what u is going to? Well, it turns out you can figure it out. It's just going to go from whatever u would be at 1, so u of 1, to u of 2. That's pretty small, so you can't quite see it, but the point is we're going to plug in these limits, 1 and 2. We've got to plug into our u equation and figure out the new limits of integration. So let's do that. 1/3 integral of u squared du. So my new limits are, for the top one, plug in 2. So we plug in 2 cubed minus 5 is 3. So that's 8 minus 5 is 3. And then downstairs we'll get plug in 1 to my u equation right here. So we get 1 cubed is 1 minus 5 is negative 4. Do those numbers look familiar? They're the exact same things I just cubed right here. So they just sort of happened. This was a negative 4 cubed. So basically the same numbers that were part of my solving process, doing it my way, we're just going to sort of like make them official by making them the limits of integration in this situation. At this point, we can do 1/3, and u squared becomes u cubed over 3. So you'll notice they get the same 1/9 that I had. Evaluate from negative 4 to 3. So that's just combine the 3s, I get 1/9 u cubed. Evaluated from negative 4 to 3. Now at this point they're going to actually plug in, so they'll get 1/9 times 3 cubed minus a negative 4 cubed. And you'll notice that's the exact same calculation that we did a second ago. And of course it's going to result in the same answer, hopefully, if you do your arithmetic right. So what happened? Instead of saving plugging in for the end, they plugged in up here to change their limits of integration to be from negative 4 to 3 instead of from 1 to 2. Which way is better? I don't know. People have different opinions on this. The thing that's nice about my way is you never have to worry about subbing in u and then du and all that kind of junk. Because I do feel like students, when they're taking calculus the first time, are usually pretty confused by u sub. So the less you can do to confuse matters by sticking in a bunch of u's where they don't belong, the better. On the other hand, when you actually go in, you know, at the end to plug in your limits of integration, having switched the limits actually does save you some work down here. I didn't have to do any math in my head down here because I'd already done it up here. And that is one way you can avoid a few errors. So really this just depends on your teacher. If your teacher is forcing you to do u sub, kind of the mathy way, and your teacher's insisting that you change the limits of integration along with subbing in u, then that's the way you better do it. At that point, you can kind of decide. But if you really wanted to, you could do the u sub and then switch everything back to x's before plugging in limits of integration. So you can kind of like combine and mix and match. Whichever way you feel like you make the fewest mistakes is the way to go. Of course, the way that gives you full credit is also important. So if your teacher gives you flexibility, by all means, do it whichever way you want. But if your teacher is one of those sticklers who makes you do it exactly the way your teacher does it or you don't get credit, that's a total bummer, and you should definitely do it the way your teacher wants you to do it. All right, another definite integral. Let's take a crack. So this one's a little bit different. Let's see. Now the first thing to realize is that this is not, in fact, there's a power rule problem. So one of the tricks, and we'll see this in upcoming video, is that when you have a root, that's really just a power rule, right? We've been doing that for a while now with integrals. So I probably want to rewrite this as the integral from 0 to 2 of x times 4 minus x squared to the 1/2 power dx. All right, so there we go. All right, so at this point, we just go to the usual thing. We've got something to a power, so obviously that's my u. So u equals 4 minus x squared du equals negative 2x dx. All right, so I need a negative 2. So integrating from 0 to 2. Now you'll notice I need a negative 2. I have the x, that's out front, but they kind of wrote it out front instead of behind. So maybe I'll just rearrange the order while I'm at it. So I'll just turn this into 4 minus x squared to 1/2. Then I got my x dx, but I just realized I need a negative 2 also. So I'm going to put a negative 2 right there, and which means I have to put a negative 1/2 out front. Because the opposite of a negative 2, the thing I can multiply it by to make it 1, is negative 1/2. So if you're going to conjure a negative here, you got to conjure a negative here also, so that you don't cheat and like stick a negative sign without compensating for it with another negative sign. All right, so at this point, do it in my way, you would just look at this and say, oh, my u matches my du, everything's square, I got my negative 2x dx, don't have to worry about it, so now I just integrate. So negative 1/2, the integral of something to the 1/2 power is just going to be that same something to the 3/2 power all over the new power, which is 3/2. Of course, dividing by 3/2 is really multiplying by 2/3. So I would put a 2/3 here to get rid of that. And it's integrated from 0 to 2. So now I've got negative, and the 2's cancel, so I got negative 1/3 times 4 minus x squared to 3/2 power evaluated from 0 to 2. Alright, so we plug and chug through this, we get negative 1/3. I'll just write the negative 1/3 once, then do the. So 4 minus x squared is going to be 4. I will plug in 2, so we get 4 minus 4 is 0. So that's just going to be 0 for the top limit. Then I got a minus sign built in. Now I got to plug in 0. So when I plug in 0, I'll get 4 minus 0 is just 4. 4 to the 3/2. All right, what is that? 4 to the 3/2 is just 4 root 4, which is 4 times 2, which is 8. So I got negative 1/3 times 0 minus 8. So that's just going to be 8/3. All right, I encroached a little bit on the space next door, so let's see what happens. All right, so that's the non-mathy way. Let's see what happens with the mathy way. Once again, same first steps. So I'll just skip those, but basically they're going to say, you know what? U equals 4 minus x squared, so du has to equal negative 2x dx. That's the step right here. The mathy person does it the same way. They realize they need a negative 2, so this step right here is exactly the same. So we'll get down to this step okay from 0 to 2. I just want to show you guys the switching the limits of integration, because that's the hard part. Times negative 2x dx. All right, so they've gotten to this point the same as we did in the previous version. At this point, they're going to stick in u for everything. So they'll still have the negative 1/2, but now they'll have u to the 1/2 times du. Now the limits of integration, we've got to tweak. So they'll take the original upper limit, plug it into u, which is 4 minus x squared, and they'll get 0 for the top limit. And then for the downstairs limit, the bottom limit, they'll plug in 0, and they'll get 4 minus 0 is 4. So that's kind of weird. It ended up being improper, sort of. We've got a 0 above a 4 instead of the normal way, but you just got to follow the math where it takes you, so we'll pretty much have to go with that. So now we got -1/2 times u to the 3/2. And then, of course, we divide by 3/2, but really that's like multiplying by 2/3. So 2's cancel, and once again we get -1/3 times something to the 3/2, which is exactly what I had down here at this step. Except now, instead of having 4 minus x squared and plugging in our old limits, we've got u to the 3/2 and the new limits, which is from 4 to 0. So just -1/3 times 0 to 3/2, which is 0, minus a -8. Oops, just -8. 4 to 3/2 is 8. We just found out. So that's just -8 times -1/3, and we get 8/3. The same way. So the point is that when you sub in u's, you got to find new limits of integration by plugging the original limits into the u equation. If your teacher makes you do it that way, again, I think it's kind of confusing. You can obviously see I'm having a little bit of trouble explaining it clearly. Also, just because it's kind of a confusing thing. Therefore, if you don't have to do it that way, I would not do it that way. I would do it the old way. Just integrate, keep everything in terms of x as long as you can. Plug in your original limits into x's. That's how every student I've ever seen does it, and that seems to be the way to make the least mistakes. But whatever your teacher says goes, because they're the one grading your papers. And don't worry, we'll get a bunch of practice on this in the upcoming videos about more U-sub problems. And believe me, man, we got a lot of examples to do. So this is going to be drilled in pretty good by the time you're done with this chapter.